Okay, so last time on simulating a quantum computer, we were planning to implement the quantum Fourier transform, which unfortunately we did not because we needed to be able to apply a quantum gate to multiple different inputs, not just the first two inputs or n inputs. And that sort of took me down a big long rabbit hole that I wasn't able to resolve by the end of last time. I did some work off stream and I was able to resolve it. And so I think what I'm going to do is just start out with kind of a review of the thought process there and what I could have done better to solve it faster, more or less. Because once I took a better approach, it really didn't take that long to solve, but I think I flailed for a little bit too long on the last stream, which happens from time to time, and it's always good to check, to review afterwards and see kind of what you could have done better. So the idea last time was that we needed to update for a quantum circuit. We needed to be able to add a gate not only say we have a 5-qubit circuit, we want to add a 2-qubit gate to it. We want to be able to add it to the third and the fourth, or the first and the fifth, or whatever different inputs, and we didn't have a way to do that yet. So last time we updated the API to take a vector of sizes instead of just the first size. And we kind of went down this rabbit hole. I went down this rabbit hole of, well, I think you probably like the approach that I took, and it is the approach I ended up using. But the idea was, okay, we already know how to add a gate to the first n inputs, and really there's nothing special about which input is which. We can permute them around all we want. So let's just permute, let's just create our gate as though it was on the first two inputs and permute things so that then it's on whichever inputs we want, which is an approach that I like. The trouble we ran into, though, was basically that it wasn't working, and it was really hard to kind of work out why it wasn't working, and the debugging loop was bad, because I was repeatedly, I was trying to write granular tests. I was looking at the output of those tests. I was walking through with the debugger, but at the end of the day, I was staring at matrices or vectors in the debugger window, and trying to do essentially head math, right? Matrix multiplication in my head, or I could have, copied them out and tried to do them really slowly, and I did end up doing some of that at some point. And that was kind of what made me realize there's got to be a better way. And so the better way, and this is almost always true, and I should have gotten here faster, is to make it really obvious what's going on in the code, which it was not, because the debugger output was, would be 64 element lists, essentially, that corresponded to 8 by 8 matrices. So, A, make it really obvious what's going on, and B, I was trying to do the swapping of qubits in the add gate function, which was just the wrong level of abstraction. Like, a swapping qubits around is something that you can do with a gate. There is a gate that permutes the qubits, and so it would have made a lot more sense, and what I ended up doing was implementing a new type of gate that knows how to permute the qubits. And then the other thing I did was to make it really obvious what was going on by implementing display, which and debug, to actually print out the contents of the matrix in a matrix format, so that I could at least print ln the matrix and see matrix looking outputs. Don't know if I have any of them still saved up here somewhere. I probably do, but now all my tests passed, so I can't see them at this point, but I'm sure we'll use this again. So by implementing display and debug for square matrix and then all of the types that use square matrix, I was able to look at the matrices I was creating. So here it's being implemented for quantum gate, and I also was able to implement and test a new type of quantum gate, a permutation. And for a permutation gate, you give which qubits need to get permuted, and then basically the logic steps through and works out using Boolean arithmetic, essentially. It works out if you give it qubits that are getting permuted, it works out what basis vectors need to get permuted and creates the appropriate permutation matrix, which is just going to be a matrix with exactly one in each column in a way that corresponds to rearranging the basis vectors. So we got that permutation matrix, wrote a whole bunch of tests, or at least a few tests somewhere. I guess one test that do a bunch of checks on permutation matrices working, and then I was able to go and in the circuit I definitely did a whole bunch of individual step-by-step tests. Can we add a gate at the top? Can we add a gate at the bottom? Can we add gates at the end that are a little bigger? Can we add multiple gates somewhere along here? And by having all of these granular tests and using the new permutation matrix type, I was able to simplify the add gate function a lot. So now all it does is basically works out, like, have you asked it for a reasonable thing? If not, scream. And then there's a simple case where you're definitely just asking for the gate back, because you're asking to add a gate that takes the same number of inputs as the circuit, and so that's just a simple case where you return the gate, and saves us having to do some computation, so we exit quickly. This next bit could probably maybe be factored down into a function, but essentially the idea is, we input some number of qubits that are going to get that where the gate needs to be. Let's see here. We input indices for the qubits that the gate needs to apply to. Those don't cover all of the inputs, and so we just compute what the qubits, like what the full set of permutations needs to be in order to make sure that every input of the circuit gets mapped somewhere in the permutation. We do the same thing that we did before, where we take an identity gate and we tensor product it with the gate in order to get a matrix of the right size that does the thing we want. And then we get these two permutation gates, one that's the inverse of the other, that basically takes the whatever qubits you want to use as an input and maps them to the first n inputs and maps the other ones in the simplest way possible. And then the inverse of that takes the first n qubits and maps them back to the input qubits that you want. And then we compose all of those into one big gate, which we push onto the gates of the circuit. And so now things like, where's the most complex test? 2 qubit gates at the end, 2 qubit base. So here's a 4 qubit quantum circuit with a C0 gate applied to the second and third inputs. So that means it's these two bases, right? Or these 2 qubits, rather. And so 0 still gets mapped to 0, 1 still gets mapped to 1, but 2 still gets mapped to 2, 3 still gets mapped to 3, because the control bit, which is this one, is 0. So those stay the same. But then 4 gets mapped to 5, because now the control bit is 1, so the subsequent bit becomes 1. And likewise, 5 gets mapped to 4, because the control bit is 1, and the other bit gets knotted from 0 to 1, and so on and so forth. And now when we run this, terminal just sits here, but hopefully, there we go, test passed. So now, in fact, all of our tests are passing, except for the 2 Fourier transform ones, which we haven't implemented yet. So today we are going to start by finally implementing the Fourier transform. Cool. So let's do that. And I want to open up the definition of that. Oh, I already have this in my downloads now. Tries to open in Microsoft Edge, which is really nice. Okay, let's take a look. Okay, so I think we started writing a test for something like this, where, so one way to think about what the quantum Fourier transform does is it works out, or maybe it's the inverse Fourier transform, I'll have to remember, is that it can help you work out this sort of phase rotation problem like this. So suppose that for whatever reason you're in this state where each of your basis vectors has been rotated by some amount times that basis vector. So your 0th basis vector hasn't been rotated at all, your first basis vector has been rotated a bit, your second one has been rotated 2 of those, the third 3 of those, and so on. Then figure out what the bit is, what omega is here. And I think it's the inverse Fourier transform that works this out for you if you set up the circuit right. Yes, the inverse one works it out for you. And so we started setting up the tests to do this, so let's continue with that. So quantum circuit, and where's our Fourier transform test? Measurement interference, Fourier and inverse are inverses. Okay, quantum Fourier transform. So we're gonna pretend that our omega is 0.101. This is in binary decimals, so this is 5/8 is 0.101. You can think about it as this is the smallest bit, so this is 101 of that smallest bit, but 101 in binary, so the smallest bit is not 2, not 4, but 8. So it's how many eighths? Well, 4 plus 1 is 5/8. So it's going to be 5/8. And so we set up the initial problem by just pushing. So we get the IFT for 3 qubits. We get our basis for a certain index, but we only want this it's 3 qubits. There are 8 basis vectors for 3 qubits. Just think about how this needs to be set up. So what I'm thinking about is, what is 0 versus 1 here? That's not 0, 0, 0. Maybe it is 0, 0, 0. Oh, because each one of these, okay. Right, so, okay, so the input is some superposition of all 8 basis vectors. But this input is saying that our 0th bit is in the superposition that looks like this. Our first bit is in the superposition that looks like this. Our second bit is in the superposition that looks like that. And then we just get to add those all together. So what does that state look like? And I know this is originally derived somehow. So this is just for each of the basis states. Rotate that many times. So I think this is what I tried to do here. So for IDX, going through each of the basis states, take it, rotate it by IDX times omega, and then we push it onto the vector. And then we mix them all together at equal weighting, and then we run it. And we expect the answer from the quantum Fourier transform, for the inverse Fourier transform, to be (1, 0, 1). Is that what we expect? So we're putting in states like this. And we expect to get 1, 0, 1. It's x1, x2, x3. Yeah, x1, x2, x3, but it's symmetric anyway, so we expect to get 1, 0, 1 back. We're not getting back 1, 0, 1 because this test is failing. What are we getting back? Let's find out. So assert almost equals. Run, and we probably have to clone here. And we'll clone here just for, I don't mind having extra clones in my tests. My tests are not going to be fast, but I want to be able to write tests fast and iterate on them fast. Okay, so this fails. Oh, it fails with not implemented. Lol. Yeah, that would make it fail. Okay, we haven't written the actual Fourier transform yet. Shocking. Shocking, shocking, shocking. Okay, let's implement the Fourier transform then. Okay, so the Fourier transform is going to look like this, which is to say we Hadamard the nth bit, the ith bit, so with n bits, we Hadamard the ith one with n minus 1 bits, actually. No, we have n bits. Yeah, we have n bits. Okay, so we Hadamard the ith one. We apply the rotation I plus 1 to the 0th and the I plus n gate, and then we repeat. So this should be straightforward. Note that in practice we don't need to physically implement this permutation, but can instead achieve the desired result by simply logically relabeling the qubits. Interesting. I'm not sure I understand that sentence. So I'm just going to implement directly. Okay, so for let's see here. There are going to be a couple of things. So it's going to be partial Fourier transform and qubits. Start IDX and it always goes to n. So that's that. And then we return a self. We're not going to create a new, yes, we are going to create a new circuit. We're going to get rid of this because it has no idea what it's talking about. We're going to put a Hadamard gate on the, so circuit dot add gate Hadamard on the start index. And then we're going to go through and do a controlled phase shift, which maybe is what I called it already, I don't remember, on, we need an omega in here. Do we need an omega in here? Yes. No, we don't. No, we don't. We just need to, yeah, it's 1 over 2 to the, yeah, that looks good. Start IDX plus I. Sure. And the other one is, it goes from 1 to n qubits. No, so it's start IDX. Oh, weird. No, this is right. So it's controlled by, so it only rotates I, and it's controlled by all the others. So controlled by all the others, start. Okay. And then is this right? Yes. Okay, so return circuit. And now we don't have a controlled phase shift, but I'm pretty sure I implemented something for this, and I just called it something different. Rotate. Did I not? Hadamard. C not. I guess I didn't implement it. Global rotation. Okay, so we'll implement the controlled phase shift. Let's do it near the C naught. Function controlled phase shift. And do we need? Just the shift? Phase. Seeing that my bitrate is dropping again. That's disappointing. But we'll have to go with it. My repeater is not doing what it's supposed to do. Okay, well, at any rate, controlled phase shift. Do we need the size? We don't. Okay, so all this should do is self. I do from back, no. New, from back normalize, but this is entirely wrong. Oh, wait. This isn't entirely wrong. Hang on. So this is 1, 1, 1, and then the phase shift. Is that right? Is that right? One qubit phase rotation gates. Sure. And then if I want a controlled phase rotation gate, it seems plausible that that's this. So, okay, so let's. Okay, so let's test this out. Controlled phase rotation gate, and let's say sure. Let's see here. Assert. Controlled phase rotation. If I do it by tau, then it should almost equals quantum gate identity 2. That's a thing. And then if we half rotate, we should have 0, 0 doesn't get rotated, 0, 1 doesn't get rotated, 1, 0 does get rotated. So it's this, and 1, 1 does get rotated. So it's this. And this should be tau over 2. Tau over 2. And that's just equal to the NOT gate. So we should be able to just say C naught. Okay. And I really thought I already had tau in here, but I don't. So let's get tau in there. And what did I call it? controlled phase shift. Shift, and quantum gate C naught needs to be a reference. Okay. Did not pass. What's the issue? Oh, sure. Okay. So we'll do the partial Fourier transform, and then let's just say unimplemented for a little while longer here, so that we can test our stuff properly. Okay, so controlled phase shift is failing. Now why is that? So what are we actually getting back from this? So we're getting back 1, 1, 1, 1. We're getting back the identity. Which is not what we expect, because the quantum phase shift rotating 180 should rotate 180 degrees. Oh. What's this? Still fails. Still the identity. Okay. Let's take a look. So we would expect 1, 1, 1, and the phase times complex of I, and tau over 2 times the complex of I is going to be, oh, it's -1. It's -1. -1 is right. Okay, so -1 is right, so I'm just wrong about what it means to rotate. So it doesn't almost equal to quantum the C naught gate. Is there a nicer way to write this? Not really. Yeah, the point is that when you flip the bit entirely, it still is the same bit. So we have, so we're trying to do the controlled phase shift, which should perform a phase shift on the second bit. depending on the first bit, but I don't really buy my matrix that I wrote down for what that looks like. So let's just see what the right matrix is. Control not, Control Z, swap, phase, controlled, phase shift, C phase, 8. Okay. So that's correct. I have the right matrix. So it just doesn't do what I think it does. Test. Controlled phase shift gate. So basically 0. So it's doing the right thing. I don't totally understand what it's meant to, what the result is meant to look like. I think the point is that the bits, okay, the measurement you would get all remain the same, because the only thing we're doing is rotating the last basis. So we should just write down what the expected quantum gate new, and yeah, that's what we would expect. And expected. Is there no from vector on this? New takes a square matrix. Square matrix has, oh, from vector normalize. Right. Okay. Cool. Control phase shift. And so now going back to the Fourier transform, now we have the controlled phase shift, and now we can do, we have to apply the partial one to each gate. So for I in 0 through n qubits, nope, we want the bases. We want each basis vector. In fact, that's true here also. 2e size dot power of this. And we should go ahead and just give this a name. Let's call this and bases. We'll say let n bases be this. And then this also becomes n bases as U32. And then Fourier transform becomes same thing here. Put that in a function, but it's a one-liner, and being explicit is somewhat valuable. Bases. Then we say let partial be partial Fourier transform. Let u2 return be self new and qubits. To return, do we want to call it composing? Let's call it appending, I think. And then we return to return. Okay. N qubits and start IDX is I. Good. And then we just need to implement append. Self and something of type self. And it doesn't do anything. And we just extend our gates. Maybe we should call it extend. And this is just like this. Okay. So now we have an fully implemented Fourier transform. Let's find out if it works. Testing with their inverses. Oh, let's get our stuff to compile first. And bases as F32. Failing to compile. Oh, no, it failed. It just failed the test. Matrix index out of bounds. Interesting. Okay. So if this is failing, let's okay. So we are trying to add a gate that's too big somehow. So start IDX plus I. Yeah, we don't want to do the whole thing. We want to do n bases minus start IDX. Right? Because for the 0 case, that's what we want to do. But if we're starting at 1 less than the n base, then we just want to do this once. 1 through 1. Do it. So if this is like 15 and this is 14, wait, then it'll be 1 through 1. Do we want to do n bases minus start IDX plus 1? I don't think so, because that makes the 0 case not work. Let's say that our Fourier transform is on 3 elements. We put in a start IDX of 0. Then we're going to get 1 through 3 here. We were going to get 1 through 8 here. Hang on. This isn't right. This is n qubits. but then we rotate by tau over n bases. Okay, and so it's going to be 1 through 3, so we're going to end up putting down 1 and 2. But then if I run this on with a start index of something, I needed to subtract off. So now if I run it with a start index of 1, it's going to go from, I need this to be start IDX plus 1 to, so now if I give it a start IDX of 1, it's going to go from 2 to 1 and from 3 to 1. And then it's going to stop. Wait, it's going to go from two to 1. We don't want it to go 3 to 1. Let's see here. N qubits minus start A. So this would be 1 plus 1 is 2. 3 minus 1 is 2. So it's just going to do it the one time, which is correct. Okay. Okay. Failed. Matrix out of bounds. Let's take a look at what's happening here. And actually, maybe I'll run, yeah, it probably doesn't matter which one I do. This one's probably easier. Fourier transform. So, n bases should be, oh, did I do 4? I'm going to do organize things a little bit here. So over here, I want my quantum, I want my test. Do it on 4. And up here, I want my okay, so n, so Fourier transform, oh, this is wrong. This is wrong. This needs to be n qubits. And then partial Fourier transform n qubits of I. And then within this, yeah. And we actually never ended up using this. Okay. Failed. Assertion failed. And which assertion is this? From int. Value is less than size. Size is 2 to the qubit, value is that. Okay. This needs to be 4, and this needs to be I. Okay. Passed. And let's check the inverse Fourier transform. Failed. Let's print something. ift.clone, run it on an input, we get back a vector. Okay, this is a vector. So this vector is very much not equal to any basis vector. This vector is some horrible mix. Okay, these are basically all 0. So this is 0, 0, 0, 0, 0. Something with a magnitude of 1. No. Something with a magnitude of root 2. Yeah, okay. So, this is not really what we were hoping to get back. Rotated bases, mixture. Okay, so let's check our understanding. So we're trying to do an inverse Fourier transform. We're trying to use 3 qubits to work out what 101 is. Where omega is 0.101. To do that, we set up the initial states. We just did it directly, so we just built this state effectively, or this state. So this is a basis-wide mixture of e to the 2 pi I omega. So rotate by omega y for each basis vector, which is what we're doing here. So we get a basis vector, we rotate by that value times omega, and then we construct a mixture out of all of that. The mixture checks that all the registers have the same number of qubits. Adds the vectors together without putting any weights on them, and then normalizes them. That seems like what we want to do. Why can't I find... Oh. Okay. So this is the resulting state, and then we're applying the inverse Fourier transform to it. And it's definitely the inverse Fourier transform we want. Yes. Hang on. Hadamard, oh yeah, because these are inverse gates. Now, okay, so 2 hypotheses as to what could be going wrong. One, which I think is less likely, is that we've implemented this incorrectly, or rather, we've implemented this incorrectly, which we then invert. We know the inversion worked right, though, because we have a test for that. The alternative is that specifying this basis and inputting those qubits is different then like initializing the register to this is different than initializing the register to this, which I think is what's going on. So the circuit diagram is saying, the 0th bit is initialized to this value. A controlled phase shift of e to the I pi is symmetric. That's probably worth writing a quick test for. Let's just do that. Oh, my cat wants out. Hang on. So, in other words, quantum gate of controlled phase shift tau over 2. How do we get a phase shift of e to the I? That's tau over 2, right? Should be almost equal to, let's see here, let reversed gate let reversed C phase be quantum gates controlled phase shift tau over 2, but then we're going to dot compose with permutation, quantum gate permutation back 1 0. Yeah, because that should give us sphere reference, because that should reverse that means we're first going to reverse the, whatever you put in, we're going to reverse the inputs, and then we're going to do the phase shift, and so at the end of it we should reverse the inputs back. So let's just pull this out and call this let's swap gates, swap gate, swap gate, could be swap gate dot compose, and this whole thing. And now we're going to say it's almost equal to reversed C phase. Which it is. Okay, nice. Okay, that was a little side test. So, what does it mean when the circuit takes these inputs? I'm not sure is the answer. So what if we apply the regular Fourier transform and see what we get out? Test Fourier transform. And we'll say what will we say? Let's put in 1, 1, 1. So let's say assert that the Fourier transform on 3 elements on quantum register basis or from int 3, 7 almost equals, and what do we expect it to equal? We expect it to equal a mixture. So let's say let expected. It's not a mixture though. I actually honestly don't understand what it's meant to. I don't understand how to read a quantum circuit diagram that has this as the output. It's saying that the coefficient of the nth basis vector in the resulting state is going to be a superposition of is it just going to be this value? I think that might be what that means, notationally speaking. For now, let's just say quantum register all zeros. Expected, and let's spit something out of this. Let's see if we're right. Run quantum register. So we run it, almost equals. That's gonna fail, but what do we get? We get an oscillating 0.3535534. Interesting. And how am I meant to interpret that? So e to the 2 pi I So e to the tau I rotated by, and all of these are just ones. So it's rotated by, okay, expected. So I expect it to be a mixture. Let's see here. What is this value? Is this 1? Is this root 2 over 2? Yeah, that looks like, or 1 over root 2 over 2. that what that is? Yeah, it's 1 over root 2. Okay. And then if you rotate that by half a pi, because 0.111 is just going to be, so this is going to be 0.1, which is just 1/2. This is going to be 0.11, which is 3/4. Then 0.111, which is 7/8, is what we would expect. So half, so tau over 2 times I so this is going to be the state it's a mixed state. So is this meant to be like 1, 0, 0? A mixed state between 0, 0, 0 and 1, 0, 0, which is with an extra rotation by a half turn, which is say a -1. But this is negative imaginary. I don't understand what this state represents. So let's see if we can work out what this state represents. So for a 1-element state, then sure, I believe you, because I know what, for a 1-element state, I know what 0 and 1 are. But for a 2 to the n value state, it's the tensor product okay, so I meant to read these as what you would tensor product out to get to an n-qubit state. So that has to be that's got to be equivalent to, like, this is a superposition of 0 and 1. This is a superposition of 0 and 2. Superposition of 0 and 4, 0 and 8, 0 and 16, and so on. And then you tensor product those together. Okay. So now when I look at the answer I'm getting out of my Fourier transform, this gives equal weight to everything, but the phases are off. And so if I want to look at, if I want to know what the phase is for the third qubit, I would look at 4, 0, 1, 2, 3, 4, and I would say, okay, that's been rotated by 1/2. And indeed, 0.1 is equal to 1/2 in binary. And then if I want to know what's going on with the second, with what this one is, I would look at what's happening with 2. And again, it's been rotated by 0.5, which suggests that it's 0.10, which is wrong, because I rotated by 0.111 to start with. I rotated by 7, which is 0.111. So I expect to get so I would have thought I could tease those apart. And the example says I should get 0.11, which would be 3/4 of the way around. And if you rotate 3/4 of the way around, you get -I and not -1. And this is -1 times 1/2√2. Okay. Am I just still not understanding what this state corresponds to? Okay, so let's add some more. Let's not make the mistake we made last time and try to debug this fairly complicated test. Let's instead simplify it, give ourselves some more expressiveness. We would like to be able to tensor product quantum registers. So let's implement that. So quantum gate, let's do, I have more quantum register tests than that, don't I? I have a bunch down here. Let's move these up to the top. And then let's do a new test. Quantum register tensor products. So, what do we expect? We expect 0 by 0 to be 0, 0. We expect all of these to do the thing that one expects. So, let's assert that a quantum register basis 1, 0 tensor product basis 1, 0 is almost equal to 2, 0. Good. Same thing. 2, 1. Good. Good and good. Basis isn't a function yet, but I keep wanting to write it down instead of from int, and so I'm going to go ahead and say pub function basis and qubits value will just alias to that other function. Self from int and qubits value. Okay, and then let's, oh wait, what? I already have basis. It's exactly the same function already. Self from int and qubits I. Okay. And then we will do tensor product. So pub function tensor product, self other, and we're gonna get something that is the multiple long. That's correct. Can we not just Kronecker product these together? Is that not a thing? Self dot register dot Kronecker other dot register. Okay. Self new normalize. This. Okay. And now test tensor product. And it's happy. Okay, good. Cool. So we can do tensor products now. So now we can go back to our quantum circuit and we can go to our Fourier transform test. And we can say that the expected is going to be 3. Let's see here. So let x0 is going to be quantum register basis 0 3 0. Let's see here. No, it's going to be a mix. Quantum register singleton of qubit mix zero, 1, 1, and then this is going to be the whole thing rotated, right? So this is going to be a mix of this and complex 1 and complex 1, and then nope, that's not right either. Qubit basis 0, qubit basis 1, weighted at 1, and complex rotation, complex exponent of tau times 0.111 which is tau over 7 times complex I. Yeah, maybe. Tau over 7. And qubit mixed. Do I need to say dot into? No, what's the issue here? Qubit mix. Integer. Let's say F32. We can say 1 dot probably. Do we need to tell it what type it is? No, we don't. Okay, cool. So that's meant to be x0. X1 is meant to be over 5. No, over 3. X1 and X2 is meant to be over 2. Because that's 1, 1, 1, that's 1, 1, and that's 1. Okay. And then let expected be quantum register mixture of x, should be x2, x0, x1, x2, and these need to be in a vector. Okay. Fails. 3 is not equal to 1. Oh, we don't want a mixture. We want to tensor product these. That was the whole point. X0 dot tensor product x1 dot tensor product x2. It is associative. And these can be references. Fails. Okay. Let's find out why. Okay, so the actual thing is this. Let's just throw another new line in there to make this clearer. Okay, so the actual is this. Minus 3, 5, minus 3, 5, so it's getting rotated each time. And the tensor product is this thing. Which seems very different. Wait a second, it's 0.11. That's 7/8. That's times 7/8. And this is times 3/4. And this is times 1/2. Which was right, but just to be explicit. Okay. pretty different. And this is a forward Fourier transform. I wonder if this needs to be x2, x1, x0. Tensor products are not commutative. Well, it's a different result, but it's not the result we were going for. Okay. This one passed, right? Yeah. Okay. Oh, okay. I now understand this sentence. The sentence is saying that you probably want to end up relabeling the output qubits. Circuit like that in 7.4 will only implement QFT M, where M is a power of 2. Well, that's not what I'm doing. Let's just do the 2 case. First. Go ahead and assume that this was the correct labeling. And this just needs to be 3/4, and this just needs to be 1/2. And then this needs to be 2, 2, 2, 2, 4, 4, 4, no, 3. Okay, so the output of this puts a point. I mean, this looks really nicely structured. This looks like garbage. So I'm guessing that the Fourier transform is working right, and that the tensor product is not doing what I expect it to. So this is saying that 0, 0 is 0.5. Which is to say not rotated at all. 0, 1 is minus 0.5. which is to say rotated, no, is minus I times 0.5, which is to say 3/4 rotated. 1, 0 is rotated by 2. It's rotated, yeah, by 2/4, so by I squared. So by 1/2, so it's rotated halfway around. So this is rotated 0 times, this is rotated halfway around, and 0, 1 is rotated 3/4 of the way around. So that's what we expect. So now why is my tensor product so busted? Inverse Fourier transform. Should be x1, x0. Because it's backwards. Not even close to looking right, though. The tensor product. Not that bad. It means x3, x2, x1. x1, x2, x3 comes out. And x3, x2, x1 goes in. So that's analogous to what I've done here. And this really seems kind of intuitive to read off. Relatively intuitive anyway. The 0th basis is rotated 0 times. The 2th basis is rotated half a time. The 1th basis is rotated 3/4 of a time. That's what I want. So here, x0 x0 should be 3/4. So I already did the relabeling myself. So this should be 0 and this should be 1. But this still isn't the right answer. We're mixing the 0 basis and the 1 basis. There's a complex weighting. We're rotating. This just is rotated by e to the tau I times some fraction. 0.11 and 0.1. I don't really believe this tensor product. is the thing. But I do believe this test and my tensor product does very little. It does very little. All it does is internally tensor products the vectors, and it gets the right answer in the test. So it's kind of hard to imagine that that's where we're wrong. Is this like some rotated result? No, this is like completely different. This is completely different. Times the rotated amount. So it's going to end up being a 1 over root 2 in here, but that's fine. That exists over here also. Right, we end up having a 1 over root 4 in here, which is just 0.5, which is why these are 0.5s. So that's correct. Don't believe this tensor product. But I'm not sure how to interpret the tensor product of a mixed state, of like multiple mixed states together. I'm worried that this is like a matrix representation in terms of some other basis or something, I guess. Is the basic concern. What is the definition of a tensor product for vectors? Interesting. Okay, we just mix. It's just P0 times the Q vector and P1 times the Q1 vector. So let's assert that. So if we take our example and we do actual is that, let expected be quantum register, new normalize, no, should have 4 elements. They should be is it suggesting this? This is wrong. We do from vec normalize. From vec normalize, and then we can do a vector of x0 yes, this. And it passes. Okay. So we really are implementing the tensor product, right? So where we're at right now is just that this identity isn't holding. So let's check this identity first. So let's test. We'll call this tensor product expression for phase rotation problem. Let omega be 1/2. Or whatever, we can make it whatever we want, right? Let's make it 1/7. Then let left-hand side be quantum register singleton of I guess mix. Let's do mix. Let's see here. Singleton. We can just say int, right? So this can be a quantum register. We can say qubit mix 0, 1 and rotate by omega. Good. We can take the right hand side and we can say that that is oh, this is only, it can either be 1 or 0. Okay, so if it's 1, then, okay, then this is literally the same formula. So let's do the broader one. Let's do 1/7. Or let's do 7 over, let's do 5 over 8. Then x0 is 1, x1 is 0, and x2 is 1. And then the left-hand side is by omega, and the right-hand side should be right-hand side term 0 to the x to the n these cycle. Oh, that's not clear in the circuit diagram at all. So this is, let term 0 is so each of these have 3 terms. N plus 1, n plus 2. So the last term is 1, 0, 1. So that's 5 over 8. 1, 0, 1. This term is 0, 1, 1, which is 3 over 8. And then this term is 1, 0, 1 again, which is 5 over 8. Okay. So then this is term 0. Term 1, term 2. I gotta go in a minute. But okay, I think even if this doesn't work, I think this is very likely to be the idea. Let's call this RHS, and then we say assert LHS almost equals RHS. See what happens here. Okay. Okay. That's not a real thing. This quantum gate composes. Oh, I never implemented that. Let's get rid of that. Okay, where is use that test. What was that test I was just running? This. Okay, those never get used. That's fine. It fails. Left-hand side. Yeah, this is just a regular old mix. Okay, I need to construct this basis. This is wrong. Okay, but I think I get what's going on now, and I have a hard stop in 1 minute. But basically, this formula here, which is what leads to the Fourier transform later, makes it clear that you have all of the, you like rotate through the decimals, whereas these gates don't do that. And so, but then again, no, it still doesn't work. It's not right, because this shows it explicitly. It's not right. Okay, well, we'll have to come back next time and keep hacking away at that. And then hopefully, I think we have the quantum Fourier transform right, so I think it's just a matter of there's something that's not quite clicked yet to get our test to pass. But it's kind of coming up with the right answer, so we'll try to get that done next time and then finally get into visualizations. Hope everybody has a good one.